Alright, in this video, we are going to review some things that we learned back in our thermodynamics and equilibrium units and start tying these into electrochemistry, because in reality, it's thermodynamics that causes electrochemistry to happen. It's the reason behind why batteries work the way that they do. So you might recall that when we were talking about thermodynamics, we looked at graphs of Gibbs free energy as the reaction progressed. And I've got the three different possibilities for what this graph looks like shown here. The first graph here would represent a reaction that has a negative Gibbs free energy. And we know that because the beginning to the ending of the graph goes down. The second graph is what the graph would look like if we have a positive Gibbs free energy of reaction. And we can tell that because from beginning to end, the graph goes up. And the third graph would be, you notice the two ends are at the same height. So this would be something that has a change in Gibbs free energy for the reaction that is 0. The other thing that we related it to is we looked at the point on the graph where the dip was the lowest. So like this point here, here, and here. And we said that is the point where the system would be at equilibrium. So in the first graph, you can see that dip, that low point, is the place where, or it's closer to where there's more products. So that means there would be more products present at equilibrium, and K would be bigger than 1. The numerator would be larger. On the second graph, that dip is closer to the reactants side of our graph, so that means there'd be more reactants present. The denominator of the K expression would be bigger, and so K would be less than 1. And if you take the case of the last graph where the dip is perfectly in the middle, that would be K equal to 1. So that's all review from last semester when we talked about equilibrium and we talked about thermodynamics and Gibbs free energy. We also talked about how this graph, if you pick some point on the graph, say like right here, any point on the graph, that tells you where you're at that given instant. And you can also talk about the slope of the graph at that point. We said it was kind of confusing, the name that this slope was given. So notice when we're talking about the lines, that was delta G naught, the change in Gibbs free energy for standard conditions, so delta G naught. But we said the slope of the graph was given this name delta G without the naught, so just plain delta G, and that is strange, but we said that is what it was, and the slope at any point on that graph is equal to delta G naught plus R T ln of Q. And we use Q because it's some point on the graph that's not that dip. We're going to use the Q expression because we're not at equilibrium. At equilibrium, this point right here, the slope of the graph would be 0, so that expression becomes delta G naught equals negative RT ln of K. And that gave us a way to relate Gibbs free energy to the equilibrium constant for any chemical equation. These graphs are nice, especially if you're a visual person, because it can help you think about where a reaction mixture is at a certain point in time and what it's going to do to get to equilibrium. So take that point that I drew on the first graph. If that point represented your current mix of reactants and products, so like say we had, 20% reactants and 80% products in our reaction mixture, because it's a lot closer to reactants. At that point, we have more reactants than we need to have at equilibrium. So at this point, Q would be less than K. The slope of the graph at that point, which is delta G, is negative, and the reaction is going to proceed spontaneously in the forward direction in an attempt to get to equilibrium. If we pick a point on the other side of the graph, say this blue point here, that would be a point where there'd be too many products. So the numerator of the K or the Q expression would be too big. Q would be bigger than K. The slope of the graph, which is delta G, is positive, and the reaction would proceed spontaneously in the reverse direction. So we can kind of use this visual to figure out how the reaction is going to shift to attempt to get to equilibrium. Again, kind of reviewing what we had talked about in the past, we talked about Gibbs free energy and why it was called Gibbs free energy. We looked at this in the fall, and we said Gibbs free energy is called free energy because it's the energy left over when you use some energy or to make sure that the entropy of the universe increases. Because in reality, Gibbs free energy being negative means that this is a process that will increase the disorder, the entropy of the entire universe. So if you've got this left, some of the energy might have to be used to make the universe's entropy increase, but if there's leftover energy, the process can be spontaneous, and then you can use some of that leftover energy to do something else. If it's not used, things are just going to get hotter, but we could also use this energy to do useful work, like make a light turn on, make your iPad run, anything that we would use a battery for, we can harness that free energy to do useful work. If you've ever taken a battery and you've connected one end of the battery to the other end directly with a wire or with steel wool, you will see that heating up of the universe that happens if no useful work's done. That's that free energy, that extra energy that's not really going to anything useful. But you also know that if you hook those two ends of the battery up to something that can do work, like a light bulb, you will get that light bulb to turn on. You'll get a fan to spin. Whatever it's hooked up to, work will happen. Now I'm going to pull in a little bit of physics here. We're talking about batteries, and we've talked about voltage. Physicists prefer to think about energy, or electrical people prefer to think about energy as energy carried by charges. So voltage is actually defined as a joule for every 1 coulomb. And so using units, we can write an expression for the standard cell potential, which we want to have in units of volt. So E, the standard cell potential, which we need to have in units of volts. You can get units of volts by taking the standard Gibbs free energy divided by something called N times a capital F. So let me talk about each of these terms one at a time. First, we know that E cell is the cell potential, which we calculated using half reactions last week. It's in units of volts or voltage, which means we need to get joules over coulombs. Over here, we have Gibbs free energy, something we're familiar with. And the units of Gibbs free energy are kilojoules over moles. Now the two terms on the bottom are new. The N represents the number of electrons transferred in the specific reaction that you're looking at. So you'd have to get that by looking at the half reactions and figuring out how many electrons are exchanged. F is called Faraday's constant. Not something that you need to memorize. It's given to you on the AP test. You probably will need to use it for some calculations. It is 96,485 C, which is a coulomb, the unit of electric charge, for 1 mole of electrons. It's saying this is how much charge is contained if you have an entire mole of electrons. Well, why do we care about moles? Because if we're gonna get units of voltage, joules over coulombs, we've got a mole here and a mole here, and they're gonna cancel out. We have a kilojoule here and a coulomb here, so this is going to give us kilojoules over coulombs. Well, you may recall in Thermo earlier in the year we had to really be careful with units. We're going to have to be careful here again that we get this unit matching to happen when we start doing some calculations in a little bit, that either one side or the other, we've got to get into joules so that the cell potential will be in volts correctly. You normally see this reaction on an equation sheet written as delta G naught is equal to negative NF E cell. But I wrote it the other way first because I think it's easier to see how it relates to the definition of volts, that volts are energy carried by every charge, the amount of energy. So what this means here, is that the cell potential is another way to quantify how much free energy that we have available to do useful work. So a 1.5 volt battery, like a little AA battery, it means it has 1.5 joules carried by every coulomb of charge, but as that battery gets used up, maybe now its voltage is only 1.3, that means it doesn't have as much energy carried in that cell. There's not as much free energy available to do useful work. And as that battery gets used up and used up and used up, as there's less energy stored in it, the Gibbs free energy goes down and the cell potential goes down, the voltage goes down. Another thing it's worth reminding ourselves about at this point is that meaning again of that little knot. It means standard conditions, which means two things. It means 25 degrees Celsius, and it means that all solutions are at 1 molar concentration. So that's going to come up as a battery goes on and is used up. Not all concentrations of all ions stay at 1 molar, so you're not always going to be at the standard cell potential. As you saw in the polo that you recently did, the cell potential can be different than standard as you move away from those 1 molar concentrations. And so we're going to use the picture of this Gibbs free energy graph that we have to help us think about what the cell potential is at any conditions, not just standard conditions. The other important thing to think about in this reaction, I don't want to get stuck in the calculations yet. We'll do an example of that. But I want you to notice that Gibbs free energy is proportional to the cell potential, but that there's a negative sign. So if you know the Gibbs free energy change at some point, the cell potential is going to be proportional but have the opposite sign. So coming back to this and adding what we have figured out about cell potential, we know, like at the first graph, this represents something that has a delta G of reaction that's negative. We know it represents something that has a K that is greater than 1 because products are more prevalent at equilibrium. And we know that delta G and E cell are proportional but have opposite signs. So this would be a process that has a standard cell potential that's positive. Well, this should match what you already know. A positive cell potential means that you've got a redox reaction that's going to move in the forward direction. That's going to be spontaneous in the forward direction. So all three of those things would mean spontaneous in the forward direction. Negative delta G of reaction, K bigger than 1, and E cell that's positive. So if we look at the second picture, this is something where the delta G of reaction is positive. This we already know is a situation where the equilibrium constant is less than 1 because reactants are more prevalent at equilibrium. Since E cell is proportional to delta G of reaction, But with the opposite sign, this would be a case where E cell is negative. So this would be a battery that really isn't a very great battery. The reaction is spontaneous in the reverse direction. Reactants are favored at equilibrium. And we won't really look at a case like the last one a whole lot, but this is where delta G of reaction is 0. So since delta G and E cell are proportional to one another, E cell would be 0 volts. Delta G of reaction would be 0 kilojoules per mole. And K would be equal to 1. We also now have these two different reactions that allow us to relate the Gibbs, or two different equations, that allow us to relate Gibbs free energy to the equilibrium constant. And it allows us, we have another reaction that allows us to relate Gibbs free energy to cell potential at standard conditions. So there is this innate relationship between delta G and K and delta E. All delta G naught, K, and E naught. So you can calculate, if you know one of the three, you can always calculate the other two. These two equations are on the equation sheet for the AP test, and Faraday's constant is also on the equation sheet, as well as the gas law constant R, so you don't need to memorize any of those. We're going to look at an example problem to show how you can use the general shape of this Gibbs free energy graph to help you think about the concepts associated with these electrochemistry problems. So it says, consider the reaction represented above that occurs at 25 degrees Celsius. So we've got a solid zinc electrode that reacts with copper in solution, so that could be like copper nitrate, for example. And this would produce zinc in solution, so like zinc nitrate, suppose, and copper would become solid and collect. It says all reactants and products are in their standard states. So standard states, that means that the solutions, the zinc and the copper, are 1 molar, and it means that it's at 25 degrees Celsius. It says the value of the equilibrium constant for the reaction is 1.71 times 10 to the 37th at 25 degrees Celsius. We could do some math here if we wanted to. We had those two equations. They're on your equation sheet. You can plug and chug. So if you know KEQ, you can use K to figure out the standard Gibbs free energy. And then you can use the standard Gibbs free energy to figure out the standard cell potential. But all I really want to know right now, this would be like the kind of thinking to have on a multiple choice question. I just want to note 10 to the 37th. That is huge. So K is really, really big. This process is going to favor products at equilibrium. It's going to be spontaneous in the forward direction most all of the time. So if I were going to just sketch, I've got a graph already drawn on here, but because I know that K is very big, I know when I'm sketching my curve here that the dip is going to be much closer to the product side. And as soon as I draw a sketch with the dip closer to the product side, it makes doing part A and part B really pretty simple. It says, predict the sign of the standard cell potential for a cell based on this reaction. Explain your prediction. Well, and it says, predict the sign of delta G for this reaction. Explain your prediction. Well, if you look at this graph, delta G, like as soon as you recognize that this low point has to be closer to the product side because K is really, really big, then by virtue of the shape of this graph, delta G of reaction at standard conditions has to be negative. And if delta G at standard conditions is negative, then, sorry, I put that in the wrong spot. If delta G for the reaction is negative, and we understand that Gibbs free energy is proportional to the opposite of the cell potential, then the cell potential at standard conditions has to be positive. Another way that you could explain this is that if K is really, really big, then the reaction proceeds in the forward direction spontaneously, and that corresponds to a negative Gibbs free energy. The Gibbs free energy, all that extra energy, is what's driving this reaction to happen spontaneously. Then it says, how would the cell potential change if the reaction were carried out at 25 degrees with a 1 molar solution of zinc nitrate and a 0.1 molar solution of copper nitrate? Explain. So if you think about this with the kind of logic that you were using in the POGL, if we compare the conditions in C to standard conditions, we have decreased the concentration of the copper. So basically decrease the concentration of a reactant. That means the reaction is going to be more shifting in the forward direction, and the E cell, and notice I didn't use the little not sign or the degree sign this time because we're no longer at standard conditions, it will be less. You can also use this graph as a visual way to think about it. So let me show you. There's going to be some point on this graph where all the species are in standard state, where Q would be equal to 1 because the concentration of zinc is 1 molar and the concentration of copper is 1 molar. So if you've got basically equal concentrations of products and reactants at that point. So if you think about, well, now we have less reactant relative to product. So thinking about the fact that reactant is here on our graph, while product is over here on our graph, we now have more product relative to amount of reactant. Our ratio of product to reactant got bigger. So we have moved ourselves this direction on the graph. So they said, okay, say it's this point right here, which they've got identified by a blue line. The slope of the tangent line at that point on the graph is less. That means that the Gibbs free energy at that non-standard condition is less. And because Gibbs free energy is, and that's a negative because the slope is negative, but Gibbs free energy is proportional to the cell potential at any condition. So cell potential is just opposite in sign, but it's still going to be a smaller magnitude, so the cell potential is less. So like this green line here, that might represent the voltage of, say, a fully energized or fully charged battery. As the battery goes on, as the reactants get converted into products, so you have less reactant and more product, what's basically happening visually is that you're moving along this graph closer and closer and closer to equilibrium. And the slope of the tangent line gets less and less and less. So the Gibbs free energy change is less. The cell potential is less. The driving force to get to equilibrium is less. The work that can be done is less. And if you think about it for a second, maybe even turn to someone near you and discuss this. What do you think happens when you get to this point on the graph here? We're at equilibrium. What is that for a battery? Basically, that is the point where we'd call the battery dead. If the chemicals in the battery are at equilibrium, there's nothing driving the reaction one direction or the other. There's no energy changes happening, so no work can be done, and that battery is useless. So the cell potential, well, and that kind of leads into part D. When the cell reaches equilibrium, the slope of that tangent line is 0. And we'll write this in red because it goes with that point on the graph. The slope of the tangent line is 0. So the Gibbs free energy change is 0. So the cell potential is 0 and the battery is essentially dead. It can't be used to do anything useful anymore. So I think using this graph can give you a way to answer conceptual questions like this that don't require calculations, maybe a little faster, maybe without having to use so many numbers and do so many calculations, perhaps on a multiple choice section. Now, it's great to be able to answer multiple choice questions, but you could also have some calculation type of questions on a free response question. So I do want to do an example of that because there's a few details that I want to make sure to point out to you. So this is a practice exercise from your textbook. It says calculate the equilibrium constant and the Gibbs free energy at standard conditions for this reaction at 25 degrees. And that's all it gives you. You might feel like at first, I don't have a whole lot else. Now on the AP test, you'd probably have to be given one other thing. The textbook didn't give it to you because they're assuming you have the textbook. But when you have a redox reaction like this, you can break that redox reaction into its half reactions, figure out the cell potential for the reaction based on those two half reactions. And once you have the standard cell potential, then you can figure out Gibbs free energy and K. So I'm going to take this and I'm going to break it apart. We had to the two half reactions, we have 2 aluminum. That, go to that. And our other half reaction is solid magnesium. Goes to 3 magnesium ions. So I'm going to go to that table of standard reduction potentials in my textbook, and that's where these numbers are coming from. The E naught for aluminum is negative 1.66 volts. And the potential for the magnesium reaction, now notice I'm going to change the sign here. In the textbook, the magnesium reaction is negative 2.37, but because this is the oxidation, it has the opposite sign as is given in the textbook because the textbook tabulated values are for reduction. So the aluminum keeps the negative sign as it has in the table because it is written as a reduction reaction, but I flipped the sign for the magnesium reaction because in this particular case, the magnesium is being oxidized. So if I add those up, it'll give me the standard cell potential for this voltaic cell to be 0.71 volts. I also have to figure out one other piece of information from here. If you think back, I had this term in, and I said it had to do with the number of electrons being transferred in the reaction. Well, if we've got 2 aluminum ions, each have a charge of 3+, we are adding 6 electrons here. Or in the magnesium half reaction, 6 electrons are being removed from the magnesium metal. So that's going to be important in a minute. There are 6 electrons exchanged in this reaction. So I know the cell potential. I can use this relationship to figure out the Gibbs free energy of the reaction. So Gibbs free energy at standard conditions is negative N. So N means the number of electrons exchanged. This is a little detail a lot of people forget to check. N is 6 in this case because there's an exchange of 6 electrons in the balanced reaction. F, that's Faraday's constant. You don't need to memorize it. It's on your sheet. It's 96,485. And the cell potential is 0.71 volts. So the Gibbs free energy for this reaction be negative 4,1,1026. Now, one other detail that often will catch people. Remember, each cell has units of volts. Volts are joules over coulombs. So when you do this calculation, this is going to give you joules over moles. Typically, Gibbs free energies are reported as kilojoules per mole, so this would be negative 411 kilojoules per mole. So again, watch those signs. We've also been asked to figure out the equilibrium constant. So we have one other relationship that we can apply here. Gibbs free energy is equal to negative RT ln of K. And again, R is in units of joules, so I'm going to use the joules term, the 411,000, when I do this calculation. R is, again, not a number that you need to memorize, but do be careful with that ideal gas law constant that units match. So the 8.314 is the one that has joules in its units. The temperature, standard conditions, so 25 degrees Celsius or 298 Kelvin. And then it'll be times ln of K. So I'm going to do some math. Got positive 166 is equal to ln of K. So K is equal to 1.23 times 10 to the 72nd. And it's also nice to do a conceptual checkpoint with yourself. Think about that graph that we just sketched. If we've got something that has a big EK, or KE, equilibrium constant, that's going to be something where this little dip is over here. That's going to be a process that has a negative delta G. That's going to be something that has a positive E cell potential. So you can use that little sketch to do a mental check. Yep, E cell is positive. That corresponds to a negative Gibbs free energy. That corresponds to a much bigger than 1K.